Hi. Today we are going to explore Part C of Chapter 1, Force. This section is all about an interesting concept in physics called uniform circular motion. Are you ready? When we think of things moving, we usually picture them sliding along a flat, straight line, right? But what happens when an object travels along a perfect circular path at a completely constant speed? In physics, we call this uniform circular motion. In this scenario, the object covers equal distances along the circle in equal intervals of time, keeping its actual speed completely uniform and steady. Here is the formal textbook definition for uniform circular motion. When a particle moves with a constant speed in a circular path, its motion is said to be the uniform circular motion. In such a motion, the particle travels equal distances along the circular path in equal intervals of time. But let me ask you a tricky question. If the speed is completely constant, does that mean the velocity is constant too? Take a second to think about it. What do you think? If you said yes, here is a mind-bending truth. The velocity is definitely not constant. But why? Remember, velocity isn't just about how fast you are going. It also depends on your exact direction. And as an object moves around a circle, guess what's happening to its direction? It is continuously changing at every single microsecond along the path. If you wanted to know exactly which way it is heading at any precise moment, what would you do? You simply draw a straight line tangent to that specific point on the circle. Look at 4 milestones on its journey. When the particle is right at point A, its tangent points straight up toward the north. A quarter of a circle later, at point B, it is shifted completely to the west. At the halfway mark, at point C, it is heading due south, and at point D, it points east. So let me ask you, if the direction is changing at every single moment, can the velocity ever be uniform? Absolutely not. Its velocity is non-uniform and variable, and according to the fundamental laws of physics, any change in velocity over time means one thing: the motion is accelerated. Even though the speed is perfectly uniform, uniform circular motion is always an accelerated motion. To make this completely crystal clear, let's do a quick comparison of this with uniform linear motion. Well, when an object moves along a perfectly straight line at a constant speed, both its speed and its direction stay exactly the same. Its velocity is completely constant, hence its acceleration is 0. This makes it an unaccelerated motion. But in circular motion, the shifting direction changes everything. Now, let's raise the stakes. What is actually forcing this object to continuously change its direction? Because, as you know, a change in velocity can never happen out of nowhere. It requires a force. When an object moves in a circle, it needs a continuous inward force pulling it toward the middle to keep it from flying away in a straight line. This center-seeking pull is what we call centripetal force. This brings us to our next critical textbook definition. A force acting on a body moving in a circular path in a direction towards the center of the circular path is called the centripetal force. Notice how at every single point along the path, this force vector always points directly toward the center. Now, let me ask you another question. Is the centripetal force constant? Surprisingly, the answer is no. Centripetal force is a variable force. This is because force is a vector quantity, meaning it has both a size and a specific direction. Even though its size stays exactly the same, its direction is continuously rotating and shifting to face the center as the object moves along the circle. Now, let's connect this straight to Newton's second law of motion. As you know, acceleration always takes place in the exact same direction as the force causing it. Because the centripetal force is constantly changing direction, the direction of the acceleration must also change along with it. The acceleration has a constant magnitude, but a continuously changing direction. Because its direction is never fixed, the acceleration is classified as a variable acceleration. This leads us to a vital conclusion. In uniform circular motion, the centripetal force acting on the object, its acceleration, and its velocity are all variable. The only things that remain truly uniform and constant is its speed. Can you spot centripetal force acting as an invisible anchor in nature? Think about an atom. What keeps negatively charged electrons locked in their circular orbits around the nucleus? It's the electrostatic force of attraction acting as the centripetal force. What about space? What keeps planets orbiting safely around the sun, or the moon spinning around the Earth? Gravity takes over the exact same job. As another example, if you tie a stone to a string and whirl it over your head, it is the mechanical tension in the string that acts as the centripetal force, keeping the body moving in a beautiful state of dynamic equilibrium. If you have understood the centripetal force, let's move on to another concept called centrifugal force. If you've ever ridden a fast merry-go-round, you've probably felt a mysterious phantom force pushing you outward, away from the center, right? This outward pull is what we call centrifugal force. This brings us to another major textbook definition. A force acting on a body away from the center of its circular path is called the centrifugal force. Its magnitude is exactly the same as that of the centripetal force, but its direction is directly opposite to that of the centripetal force. In plain English, while centripetal force pulls the object inward toward the center, centrifugal force appears to push it straight outward. Here is another question for you. Is centrifugal force the equal and opposite reaction to centripetal force? Be very careful here. The answer is a big no. Why? Because action and reaction forces must always act on two completely different bodies. Instead, centrifugal force is a fictitious or virtual force. It only appears to exist to an observer who is spinning along inside the rotating system itself. To understand this illusion clearly, let's look at a classic textbook experiment. Imagine a ball tied to a string, moving in a circular path on a rotating merry-go-round. Let's look at it through the eyes of two different people. Person M standing completely still outside on the ground, and person A standing right on the spinning platform next to the ball. For person M on the ground, the explanation is simple. They see the ball moving in a circle because the tension in the string is constantly pulling the ball inward, providing the centripetal force. But what does person A see, who is rotating with the platform? As the platform spins from position A to A prime and A double prime, the ball moves right along with them. To person A, the ball looks like it is sitting perfectly stationary right in front of them the entire time. So how does person A explain why the ball isn't moving from their perspective? They have to assume that two forces are balancing each other out, the inward tension of the string and an equal and opposite outward force pushing the ball away from the center. These two forces cancel each other out, making the net force 0. This is why the ball appears perfectly stationary to the rotating observer. Now, let's see what happens if the string suddenly breaks while the ball is at position P. What do you think our two observers will see? For person M standing safely on the ground, the truth is instantly revealed. The moment the string snaps, the inward centripetal force vanishes. Without that inward pull, the ball immediately shoots off in a straight line along the tangent path, PT. But what about person A on the spinning platform? As person A continues to rotate to positions A', A double prime, and A triple prime, they look out and see the ball moving to positions P', P double prime, and P triple prime. To them, the ball doesn't look like it's traveling in a straight tangential line at all. Instead, it looks like the ball is flying radially away from them. To explain this strange observation, person A has to assume that a powerful centrifugal force acted on the ball and pushed it away from the center. So, what is our final conclusion? Centrifugal force is completely fictitious. It is a virtual force that doesn't actually exist in reality. It is simply a clever mental framework used by an observer inside a rotating frame of reference to understand and describe the unique motion happening around them. That brings us to the end of this session. Please remember to like, subscribe, and share your thoughts in the comments. Thank you so much for watching, and see you next time. Bye.